I am pretty excited to be living in this age because I simply think that the theory is finally coming into convergence. Artificial intelligence has been here since, like, when, the 50s or something, where I think it was like 1954, which was the first time AI as a term was first coined. But it's really happening these days. It's becoming reality. It's applied everywhere, specifically in public safety and national security. And that's what I want to talk with you about today. So artificial intelligence is simply the idea of having machines achieving human-level intelligence. Machine learning is a subfield of AI that's about learning from data to derive rules and extract patterns instead of being explicitly programmed. And deep learning is one type of machine learning that's recently becoming really good with high-dimensional data, extracting insights from such high-dimensional data like videos, audio, and text. And you might be asking, what does this have to do with ArcGIS? In fact, we have been building machine learning tools, as we're going to see, since years. It's not new for us. And we have added new capabilities as well. And the bottom line of what you can achieve today with AI and ArcGIS is three things. First, you can use it to extract sophisticated insights from high-dimensional data like images. You can detect objects and features from aerial imagery, drone feeds, video feeds. We have done a lot of projects with these kinds of data. And you can bring the spatial analysis to life. So talk about detecting buildings, damage, roads, swimming pools, you name it. Anything that a human being can detect under 1 or 2 seconds, the rule is we can generally automate it through AI if we are providing good training data, as we're going to see. The second thing is prediction. Predicting geospatial events, predicting events that happen in a location. Talk about events that have geospatial factors leading to it, like crimes, or road crashes, or water pipe failures, or 911 calls, you name it. The third thing is finding sophisticated patterns and hidden patterns in the data. There is a specific class of machine learning called unsupervised learning, which is about finding deep patterns using clustering techniques, as we're going to see. So the first thing I want to mention is we have machine learning tools in ArcGIS today, tools that can help you with classification, clustering, and prediction. And in addition to that, we provide integration capabilities with deep learning and machine learning frameworks. We do this actually by two things. First, the Python API, the ArcGIS API for Python. I'm sure you have heard of it. The second is the R-Bridge. So most of these deep learning, machine learning frameworks, whether they are open source or commercial, are Python-based. And we're using the Python API to make this integration happen. And if you're using R, we have the R-Bridge. And I want to start today by talking about an example of such integration, using artificial intelligence for disaster response and damage detection. So I want to begin with this. The idea of responding to damages, let's say damaged structures after hurricanes, is a challenging problem. We have limited time and resources. We usually need to analyze massive amounts of imagery to understand where this damage took place. And it's not only about detecting damage, right? We need to take actions. We need to send resources. We need to optimize resource allocation. We need to understand the level of damage, et cetera. We are proposing an AI end-to-end framework methodology to deal with this problem, mainly through 4 main steps. The first thing we're going to do is using deep learning to detect damaged structures. The second thing is using deep learning again to detect damaged roads, to understand which roads are passable and which roads are not. The third thing, we want to start making some actions. So we're going to see how we are using Network Analyst and other tools in ArcGIS to optimize resource allocation. And finally, we're going to see how we're using Operations Dashboard to provide real-time situation awareness and field tasking and resourcing. So why don't we leave these slides and go to a demo? So this is NOAA's public imagery after Hurricane Mikhail, and you can start seeing the level of damage here. The first thing, if we want to have a deep learning model classify buildings or understand which buildings are damaged or not, we need to provide it with some examples. We call this the training data. Think of the training data as something like this. Hundreds of images of buildings and a label that says whether this building is damaged or not. Now, how can we achieve that quickly? We have tools in ArcGIS that can help with this. First, we're going to label some buildings. We're going to draw polygons around some of these buildings and classify them as damaged or not. You can do this through any kind of feature class or the training sample manager. But here's the thing. When me and my team were dealing with this problem, we really needed to make this happen fast. So we needed to crowdsource the labeling. And for that, we have built an app using Web App Builder for labeling, where a lot of people from different teams can collaborate on this process. This app actually is very simple. It takes an input feature layer for the building footprints, and you go on and start labeling. Let's say this building, for example, is damaged. You click on it, you classify it as damaged, and you save this, and it's going to reflect. Now, imagine a team of 10 people, for example, doing this. You can do it really fast. Once you do that, we're going to get back to ArcGIS to see how we can export this in a usable format by deep learning. So we have a new tool called Export Training Data for Deep Learning. Let's have a look at this tool. So export training data for deep learning is going to take mainly two inputs. First, it's going to take the input raster, which is known as imagery. Second, it's going to take the input labeled class, the kind of labels we have been creating right now. And we're going to define the kind of output that we need, label tiles. And when you run this tool, this is going to be basically the output. You're going to end up with a folder with a lot of labels that you have been creating, and each image is going to have its own label. This is exactly what deep learning needs to start training. Now, we are going to train a deep learning model in ArcGIS notebooks, which is a very interesting offering, bringing the power of Jupyter Notebooks inside ArcGIS. And Jupyter Notebooks, if you don't know it, is a very famous way to do data science and machine learning. It's a way where you can write code, see the results, and import a lot of data science frameworks. So what we're doing here is that we're taking this imagery, and we are writing some code to train a classifier, train a model. And this is the neural network. These are the architecture of the neural network. And once we have a trained model with good performance, now it's time to start consuming it inside ArcGIS. So we have developed a new GP tool that can help you use deep learning inside ArcGIS. And this tool is called Detect Objects. So Detect Objects using deep learning is, again, going to take two inputs. The first input is the imagery, and the second input is a text file. We call it the Esri model definition file. It's basically a wrapper around the model. And once you run this tool, this is going to be the output. So we have trained the model, and we have ran the model against this part, and these are the results from the model output. It has classified many buildings, as you can see, as damaged, and some of them are not damaged. But maybe you can look into this and say, OK, this is a small set of buildings. Why don't I just go and have my team label it manually? Because deep learning's power is way beyond that. It's about scalability. It's about doing a whole county, for example, really fast. And that's what we have done here with the majority of Bay County in Florida. So these are the results when we have ran the model on a wider area. Imagine having these results in 15 or 20 minutes real quick. And we have multiple experiments where we have taken this work into the cloud using ArcGIS Enterprise with 4 raster analytics servers to parallelize the detections, if you will. And we have cut down the time for a massive area from 4.5 hours on a local machine to only 20 minutes. So that's the real power. Think of deep learning right now, or AI in general, as automation on steroids, right? So it's not magic. It's not really something new. It's basically automating what we have been doing at scale. Now, when we've been talking about some customers about this problem, they mentioned that it's not only about buildings. It's really about roads as well. Because eventually, to respond to this kind of emergency, you're going to take roads, right? So we need to understand which roads are damaged and which roads are not. So we have done the same thing with roads. We had a web app builder app that will help classify these roads to prepare training data. And again, it's super easy. You click on the category, and let's say this part is damaged. You're going to draw a polygon here. And it's going to label it as damaged. And you're going to give it a class. And once you finish, you're going to end up with these labels. We're going to take this again in ArcGIS notebooks, train a deep learning model. This is what we are asking the model to do. Take an input imagery and define which part of this road is damaged. And we have trained a model, and again, taking it back to ArcGIS, using the model for inference, that was the result. This is the output from the model. You can see that this is pretty accurate. It's really detecting the debris or the damaged parts of that road. So wrapping up, what we have been doing so far is we have trained a deep learning model to detect damaged buildings. We have trained another model to detect damaged parts of the road, and now is the time to start taking some action. And to be honest, that's the part that really excites me about ArcGIS. It's about acting on the insights from AI. Because honestly, training a model is not that hard, but doing actions is closing the loop, if you will. So what we're going to do here is we're going to publish these results in ArcGIS Online and start using the routing services to see how can we optimize resource allocation. So this is a map showing impassable roads due to debris and impassable roads due to road damage. And we're going to see a scenario where we are using routing services to help allocate resources. So these are damaged structures that the model has identified. This is a fire station here that we want to send resources from. And that's the optimum route, given that a lot of other routes are damaged. And it can also optimize the stop sequence. If you're using this locally, you can use Network Analyst for that kind of flow. So this is not only the end. This is an operations dashboard that provides real-time situation awareness. You can see how many roads are blocked, how many roads are damaged, how many buildings are damaged. You can send inspectors to the field. You can, in real time, see what's happening. Like, here's an inspector. He's inspecting this building. Here's the results. We have 5 active workers in the field. So back to the presentation. If you think about this, this is an end-to-end workflow. This is a workflow that has dealt with imagery using image server or image analyst, and then prepared training data, and then training a deep learning model in ArcGIS, and then consuming this model and detecting the results and having these results happen at scale, and finally building on that and building some information products. That's the real power that we are providing, end-to-end workflow, not just models, not just deep learning. And that's why I'm personally very passionate about that. Now, that's an example with imagery, and that's only one part of what we are doing in Esri regarding AI. But we're also doing a lot of stuff with vector and feature data as well. And that's what I want to talk with you next. So what we are going to see right now is a great capability called the space-time cube. The space-time cube is, let's say, a derivative out of the hotspot analysis, adding the time component to help us find statistically significant clusters in our data. In that case, we're going to deal with 911 calls data that we're going to see in the demo. But before doing this, I want to really quick wrap up on the concept of a hotspot. A hotspot is not a heat map. A hotspot is simply like this. This is a map for some place. This is a feature. A feature has a value, let's say the number of 911 calls. This is a neighborhood around the feature. The way hotspot works is that it takes the neighborhood, and this is the whole study area, let's say a whole state or a whole county. And then it compares the neighborhood with the study area to see if it's statistically or significantly different, higher or lower. And significantly here is very important. We are using a statistic called Gettys-Ord GI star statistic. It's a famous statistic that you can read a lot about online. We're providing a lot of resources about it online to understand if this change is significant or not. Because you can look at something with your eyes and say, yeah, this is high, this is low. But this is a little subjective. If we want to have this objective, we need to use statistics. And that's the way it simply works. If this part is higher than the whole study area, it's going to classify it as a hotspot. And vice versa, right? So it's going to keep iterating for different parts and different features, calculate the difference between, or see if the neighborhood is statistically different from the surrounding area, and classify the whole area into cold and hot spots. Now, what if we want to add the time component to this analysis? Because near and recent things are more related than distant things, right? So imagine if you have a layer of 911 calls, and you keep adding other layers for every month, or every hour, or every week. You're going to end up with something like this, something like a cube, by adding the time dimension to the location dimension. Your data is going to be organized in some sort of a cube that has time steps and spatial steps. Now, the time steps could be months, like in that case, and the spatial steps could be like 10 kilometers, miles, meters, you name it. You're going to have bins, location, and time slices, and you're going to be able to calculate these counts as a first step. But machine learning is not just about aggregating counts. It's about finding patterns. And that's when we want to apply the same concept of hotspot, but from a temporal perspective. Now, this is the way hotspots were calculated, right? It takes a feature, it sees the neighborhood, it compares it with the whole study area, right? Now, what we are going to do is we're going to add the time step. Let's say you add a time step of 1. You want to compare each point with the month after it and the month before it, or 2 months after it and 2 months before it. It's going to form a subcube that's going to keep moving inside of this grander cube to understand if this cube is significantly different from the whole study area. And that's going to lead to this. Different cubes are going to have different values and with the time component. And you can see here that we're going to have like almost 12 different types of hotspots, right? So for example, the first one is very interesting, new hotspot. You can notice this in the column here, the second one from the bottom right. So it has been random as gray color, but finally it's turning to a hotspot. So something started to happen recently, turning this into a hotspot. This is something that we can consider for tactical use. So this type and the intensifying hotspots, for example, is the same thing, right? So intensifying hotspots, it has been there, a hotspot, but it keeps increasing. So something is happening lately that is driving this to increase or to appear a new hotspot. So we can consider tactical response. We can allocate more resources to these areas. This is different from the persistent hotspot, for example. A persistent hotspot, you can see it here, it has been there and it's increasing. So tactical response is not going to be of value, to be honest. It's more, we need to have more strategic response to that. Sending more resources to this area is not going to solve it. It seems that it has an embedded issue in it. And you can reverse engineer this and think from another perspective, like for the intensifying cold spots. So it seems that some tactics that we're doing are finally resulting into success, significantly less crimes or significantly less 911 calls. So let's see what are these tactics and replicated elsewhere. So why don't we see a demo for that? So these are 911 calls in Baltimore, and you can see that they are a lot. And we want to use the space-time pattern mining toolbox to understand these patterns. So the first thing we're going to do is creating a space-time cube by aggregating points. So the space-time pattern mining toolbox, you have a lot of tools under it. That's the first tool. And this tool is going to take and input the feature layer of these calls. And you're going to define the time step interval. It's the temporal jump, if you will. Like, are you willing to have it as months or weeks or hours? Here we're defining it as 1 month. And the distance interval, 250 feet. Once we run this, we are going to have a space-time cube that we can visualize. If you want to visualize it, you're going to choose another tool called Visualize Space-Time Cube in 3D. This tool is simply going to take the input space-time cube that you have just created. You're going to define the cube variable that you want to aggregate or do summary statistics for. And once you run it, that's going to be your output. A 3D cube showing the counts, if you will, the aggregates. And you can start, even without using any machine learning here, you can start seeing some patterns. Like there is significantly high amount of crimes in downtown here and maybe in some peripheral areas. Now let's get to the other part, which is using the emerging hotspot to create the 12 different kinds of hotspots. For that, you're going to use another tool called Emerging Hotspot Analysis. And you're going to define the variable that you want to analyze. In that case, it's the count of 911 calls. We're going to define the neighborhood distance as 750 feet and the neighborhood time step as 2, right? That's going to be the output out of running this tool. And let's spend some time to understand these results. First, we can see some intensifying hotspots here. And as we agreed, intensifying hotspots have been there, but they are increasing significantly. Now, it seems that there is something recent happening there that we need to understand. Second, if you look at South Baltimore here, these are new hotspots. So they have been random for a decent amount of time, but suddenly something is happening that is turning this randomness into a hotspot. You can continue doing this actually by seeing that, for example. That's an intensifying cold spot. So we have been doing something recently that has resulted into significantly less amount of 911 calls. So maybe we can think of how to replicate that. Now, this is a 2D experience, but you can see it in 3D as well, right? This is useful because you might want to dig deeper into okay, when exactly did that change started to happen, in which month, in which time, in which area, and you can start seeing what actions you have been taking that have led to that, or what other incidents have led to that. But the beauty about ArcGIS is that both 2D and 3D can coexist, right? So why don't we link this with the scene, with the analysis results, and start seeing some interesting views? So let's bring this here. And let's go to the new hotspots, for example. Oops. So we can see here that these are the new hotspots. And we can see that they have almost been gray, which is random. But finally, they are turning into hotspots. And we can start seeing like which month that occurred. Is it the last month, the pre-last month? And the list goes on. So that's a very powerful tool that's using sophisticated statistics in the back end to provide you with interesting insights. And that's only one example. We have a lot more other examples. We have tools that can help you make predictions, find clusters, make classifications. And we have these new deep learning tools that can help you do end-to-end imagery workflows. This is just the start. I really can't wait to start seeing how you guys are going to use these tools. We have another session tomorrow in the advanced session breakout that we're going to showcase how we're using deep learning to optimize police patrol allocation. I really invite you to attend that. Thank you so much.